So, at Hemlock Semiconductor, we're one of the world's largest producers of polysilicon. Now, polysilicon is used everywhere in microelectronics to make capacitors, to do MEMS, but really, it's the foundation for all solid-state microelectronics. We take polysilicon, shown here as a bunch of rocks, which we make at extremely high purity. We're talking parts per trillion atomic. So it's a drop of oil in a 10 million gallon oil tanker type purity level, right? Very high purity. They're put in bags, and then they go out to the people who make wafers, silicon wafers. These silicon wafers, of course, are what all solid-state circuits are built on, right? Microprocessors, power devices, memory chips, ASICs, you name it. And people who make these wafers also have to make them at very high purity and very high consistency, hence their specification to us to do the same. And they get very nice electronic circuits. This is very interesting to me. I love this slide because if you look very carefully, this is the crystal puller, where they pull state-of-the-art 300 millimeter silicon crystals for wafers. And to give you an idea of the size, there's the little Japanese fellow sitting right here. These are very, very large pieces of equipment. Of course, polysilicon today is also the foundation for all solid-state energy generation. All our solar cells that are made around the world today start with polysilicon. Again, they take any process, polysilicon, they melt it, form either single crystal or multicrystalline ingots. These are cut into what they lovingly call bricks. You don't know why they do that, but they call them bricks. The bricks are made into wafers, which are fabricated into solar cells and go into giant solar energy. So, polysilicon has touch points everywhere in electronics. And Hemlock's been servicing the electronics industry since really the beginning of all solid-state devices. Early transistor work going back to since 1961. And the plant has just grown and grown and grown. Extremely large size. So the key to making polysilicon is a technique called chemical vapor deposition. I don't know how many people here are familiar with this technique, but it's relatively simple to understand. We take some gases, these are silicon gases. Generally, they're a gas class called chlorosilanes, so they're molecules with silicon and chlorine on them. And we put them into a reaction chamber and heat them to the point where they break down. The reaction products are then condensed onto what we call a seed or a substrate, depending on the application. And then we get the byproduct gases off, hydrogen chloride, and those kind of things. Really, these CVD processes, just like the polysilicon, are the most important process in the fabrication of any microelectronic device. And in most cases, they're practiced under very ideal conditions. Gas flow is very smooth and laminar, very controlled. We grow on two-dimensional surfaces like a wafer or a plate or anything. This is the most common use of CVD. At Hemlock, we don't do it this way. Because of our scale, we have to do things a little differently. What we use is something called the Siemens CVD system. And the first Siemens reactor was developed, no surprise, by the Siemens company in Germany in 1962. And it's basically a little bell jar with some filaments made of polysilicon. They're plugged into an electrical source, heated up like the filaments in a light bulb. The gases go in the reactor and break down and deposit on filaments, and we make rods. In 1962, the rods were about 1 millimeter long. By 2012, or 1 meter long, they've grown to 3 times that size. Again, you see our little fellow here. And this particular batch is 7 tons of polysilicon per batch. And then you gotta ask the question, how do you move 7 tons of silicon that are attached by a tiny little rod at the bottom without killing yourself? If this falls on you, forget it, you're done. And this guy obviously has no fear. He's pretty confident in this reactor. This is where the black art starts, getting the polysilicon from here into the format I showed you in the previous slide, which are rocks that we go into bag. And we do this all without contaminating it at all. So it's most pure here, part per trillion impurity levels. We get it into the bag and get it to our customer and maintain those part per trillion. It really, all of the technology we use are the same technologies, the Intels and the TSMCs, all the major microelectronics manufacturers, we all use the same methods to control the purity. spend an immense amount of money. So how do you run this reactor? As I was talking to you about before, most CVD process is very controlled, planar deposition. This is a 3D monster. And by the way, we have to do it at extremely low cost. Now, one other thing I'd like to point out here is these reactors are basically light bulbs. Like I said, we put a big bell jar over it, we light up the filament like in a light bulb. So we do it at high pressure and vacuum. Takes an immense amount of energy to run one of these reactors. So much so that today Hemlock is the largest single user of electrical energy in the state of Michigan. Factoid I just heard not too long ago was our energy usage at Hemlock exceeds that of Ann Arbor, Lansing, and Jackson combined. Give you an idea of the scale. No surprise, and this will become part later, energy is one of our highest cost components of our manufacturing. So we become very concerned about the cost of energy and wasting energy and doing all that. So this is going to be a key part of our interest and why we want to get into these advanced analytics. So again, compared to the planar reactor, right, we have to use a lot of power. So when you look at this reactor sort of top down, it's a little more difficult to run than what the guys who make silicon devices. There's a lot of interaction. It's a big 3D structure. And once you start flowing gas over 3D structures, it gets very turbulent and things don't go where you want to go. And we have to power this with a multitude of power supplies. So we have a lot of inputs and outputs. And the process has to be tuned very specifically to deal with the turbulent gas flow and temperature variations and radiation effects. And we want to grow really, really fast, because if we don't grow fast, it costs us more energy. So when you do that, the gases start to turn into dust, and you get dust storms in the reactor, and that ruins the surfaces of the polysilicon. All of this gets managed, and it becomes a real challenge to keep this plant running consistently. So let's talk a little bit about the scale of polysilicon manufacturing in the world today. There are really 3 levels of plants that you find around the globe. There are these small plants. Most of these are the older businesses, and their mass output per year is somewhere around 20,000 tons. When you usually think about tons, all you think about is rocks, right? Rocks and ore and things like that. But we're producing a very highly engineered material at this rate. And these small plants generally will service the semiconductor industry. Some of them are startup plants that service the solar industry. The medium-sized plants, where Hemlock sort of falls into play, right? These are in the neighborhood of 40, 50,000 ton a year, again, servicing both semi and solar industry. And then there are now some giant plants in Asia that are in excess of 70,000 ton a year. And they're really driven at servicing the solar industry. Now, how do you run a plant like this? You got to have a lot of chemical. We're going to get 70 tons of solid from gas. Well, now we're talking a lot of gas, right? And really, this is the equivalent of dozens of large chemical tank trucks a day going in and out of the plant to bring the chemical we need to run the reactors. And it takes many, many of these Siemens reactors to produce this volume per year, right? What I talked about is 7 tons roughly to run. You can divide 7 right here, 10,000 runs a year of 7-ton reactors to fill a kind of plant that size. And as I mentioned, it's extreme electrical energy use.
Just a quick question: where do the input gases, the chemicals, come from?
In our case, we make them. I'll show you in the next slide. One of the reasons Hemlock was formed as a subsidiary of Dow Corning originally, now Dow is the intense need for chlorosilane chemicals and to make silicones in Dow Corning's core business. And basically silicones start with chlorosilane gases too. They take metallurgical grade silicon, grind it up, put it in what's called a fluidized bed reactor. We heat it up and we get chlorosilanes out. And these are the feedstock for our plant as well. And to get them to the CVD system, of course, you don't get the one you want out of here. You get a hodgepodge of molecules. So we got to go through all kinds of distillation and filtering and everything, and mixing with hydrogen, and finally it gets to the reactor. And now, again, we're in a commodity business state almost now. We don't like to waste silicon. Most CVD processes run about 10% efficiency in most companies. They throw the gas away, the other 90%. You're making a microelectronic device like a microprocessor. You can afford to throw it away. We can't afford to throw it away. So the molecules that come out here, we bring them right back into our chemical plant, the refinery, and we try to capture every one of them. And today, Hemlock, literally, we run at over 99.99% recovery rates of silicon. So almost every molecule, every atom of silicon that comes in with the chlorosilane gas ends up in a polysilicon rounds. Now, this is a sort of baseline model for the plant. The reality of the situation is one plant is really many of these. We got them all. In fact, at Hemlock, we run 500 acres on 500 acres. So we have these plants, you know, the first one, you built the first one in the 60s, and they multiply and proliferate. So now we have the challenge of making the same thing in bunches of factories and controlling these all to get exactly what we want. So what's involved with those challenges, right? Well, first one is scheduling. You got so many people, right? These reactors are pumping out 5-10 tons a batch, and you got to get it out of there fast, so you can turn the reactor back on and make another 5-10 tons, and that takes people. So we got to get the people in the right place, and you know these are very large systems, so there's a lot of safety issues involved. We run them on hydrogen; they have to be purged. They're hot. We got to wait for them to cool. And scheduling and making sure that we turn over these reactors as fast as possible to get our maximum production efficiency is very challenging. Because at the same time, we're worried about, well, I'd really like to run my reactor when electrical rates are cheap. But, you know, the rates fluctuate more often than our processes turn on and off. So there's a real critical balance in there. Where our whole goal really here is to minimize our costs, and we want to get the maximum yield out of our CVD and gas management processes. So balancing all of these operations and all these plants scattered along our site is very, very difficult. What's more, once we get the material out of this reactor, we got to test it. You just can't look at it and say, yep, man, part per trillion, we're good to go. No. We go through intensive analysis to get these measurements. And today's state-of-the-art equipment, whether it's mass spectrometers, electrical measurements, however we do this, every one of these units, we run at its bottom end. So we run a lot in the noise. So when we see the material as suitable to bring to our customers, usually it's because we can't measure it. And then there's some fraction of it that's we can measure and we know that's bad. But these tests take a long time. We got to do a lot of sampling. So the cycle time for when we start up one of those reactors to the time we can actually allow the material to go to our customer, it can take a week. Yet at the same time, they're running and running and running. So it takes a few days to figure out you got something good. By that time, you've made hundreds of tons of material. And if it's bad, then you got to worry about the 100 tons of material you made. After you took the time to take the test on, you can end up with a disaster very fast. So monitoring all of this is very challenging. We want fast turnaround. We want fast feedback. We want to understand cause and effect relationships as fast as we can between all the inputs and outputs of our plant. And it's literally buried in mountains of data. And how do you do that in the most efficient way? Well, historically, it's done manually. People download data from the database, you know, they put it in Excel spreadsheets. Everybody's got their own methodology. And we you know, sort of chugged along for almost 50 years or more, doing it this way. But there's got to be a better way. Data analytics. Hallelujah. There are ways to get at the data in large quantities. And in the beginning of, end of last year, basically, we made a value decision to make a large investment in data analytics capability for the first time. So that we can literally tie all our data sources together into one giant data source and start to analyze it to improve feedback time, get more insight in the plant, manage our operations better. But we are a bunch of physicists and chemists and chemical engineers. We're agreeing in this. We have some very nice help from our software providers, but we want to move very fast while our learning curve is difficult. we got to run a plant, we got to make money for the business, we got to get material to our customers. So how do we learn and how do we capture the advantage of the capability faster than we can? That's part of the reason why we're here. So now I'm talking to the experts, right? Machine learning. We know companies have started to parlay this. Companies like GE and Siemens, who are heavily integrated in manufacturing plants around the world with their systems, their control systems, have now been exploiting these software tools to optimize manufacturing operations. From everything to looking at variability, to identifying means for doing maintenance to keep uptime up as large as possible, and from understanding how to schedule, how to get the product out to the customer faster and more efficiently. Really, there's many, many applications that have been published on how these tools can make step change performance in manufacturing. So we are in the midst of a conversion of our culture. We're bringing in these new technologies, and then what we want to do is, of course, I don't have to tell all of you this, if you wait a year, all the technologies are better than you wait a year. So we don't have the capability to learn, parlay, and keep up. We need help. We need to partner with people and groups that can help us stay on top of this and make sure we're getting the most out of our technology and really driving our plant based on the outputs from this. And today, our plant, I think the number our IT group told me is we have over 1,000 sensors bringing data into our databases constantly, 24/7, 365 days. Plus, on top of that, those sensors that watch our plant to make sure we don't kill ourselves and all our neighbors and everything's running, we have all this data on materials analysis. We're monitoring the chemicals we put into the plant. We are monitoring our logistics and scheduling to make sure the plant's running efficiently, and we're making sure the product meets the customer needs, and all of this has got to be studied all the time. And the faster we can get feedback, the better we can run our plant and become more efficient and sustainable. So from our perspective, this is a textbook application of the utility of machine learning to give us the insights we need to get to that next generation capability. By the way, in the United States, there are only 2 such plants. There's the one in Hemlock, Michigan, which is outside of Saginaw, and there's one in Alabama. That's outside Mitsubishi. The rest of them are overseas. And we employ effectively almost 1,500 people to keep the plant running. So we want to be successful. We've been successful for a long time, but we know in order to compete and be sustainable, we have to change the way we do our work. So, why am I here? Because I want to talk to experts. I'm interested to meet people who can help staff our organization and make us world-class in the use of data analytics and its tools, and establish partnerships to make sure that we stay on the cutting edge and ahead of our competition and maintain our competitive position in the market. So we find experts, we staff the organization, we establish partnerships and learn, and we just want to keep repeating that cycle over and over until we hit steady state and wait for the next new technology. And that's why we're here today, and I'm very excited to talk to you all about it. If there are any questions, I'd be happy to answer them.
When you're looking at, figuring out how your plant's operating, say you're doing theories or something, do you typically find that it's a long-term change that you're looking for, or is it something abrupt that happens?
Generally, when we have a process go out of control, it's abrupt. But that's just because they take time to build up in the plant. So by the time we see an abrupt change, an undesirable abrupt change, we've been contaminated for a long time. That's part of the challenge, right? There's a huge latency. There's a latency on the contaminants propagating and accumulating in the plant, and there's our latency in doing testing to find out we actually got a problem. So this can stretch out weeks. And usually then, you know, you got some hindsight, you can go back and say, well, it probably started back here. But by this time, we've made hundreds and hundreds and hundreds of tons of material that may be no good. And the financial impact of that is disastrous.
What's your yield in terms of the parts per billion? The material you make, percent?
I mean, it varies on the target specification, but I can say confidently we will run between, I mean, it depends on the yield you talk about too. So we have the yield of impurities in the, what I call the intermediate, which is the rod. And then everything we do to process that rod into the form factor that's got to go to customer contaminates it more. So we have yields at all these different stages. Our rod yields are usually on the high end. You know, they're well in excess of 70%. But that can deteriorate. Getting all that material, the desire is get all that material into the bag, into the customer. That don't happen because contamination proliferates as we like. Depending on which product it is, those yields can be maintained or they can drop off.
Some most critical thing you're trying to achieve with this more efficient data analysis is that they shorten the time span catching something wrong.
That's certainly one element of this, one very important element. Another one, of course, is to start to tell us by looking at this immense set of data we have, how are these things accumulating? What's driving the variability? You know, we can have one building that'll just go down the toilet, and the rest of the plant's running fine. But you know, we're basically a giant CVD plant that is next door to a giant refinery, right? And the refinery, it's, you know, it's a rat's nest of piping, and you know, it's not a one refinery for one CVD building. No, we don't have, it's not matched up because, you know, when companies grow, you just shoehorn things in to get production going fast. So we don't have this wonderful laid out refinery CVD building. I know it's construed, and it makes it hard then to find the cause and effect on such a large scale when they're not interlaced in a very even way.
So I want to ask about the data quality. So you have all the sensors. So those sensors are really accurate, or they have some kind of outside detection? How accurate is the data?
Well, the sensors that we use to monitor our operations, they're pretty accurate. We don't find that they mislead us in many ways. Where the accuracy and precision starts to falter is in the test sensor, because we're challenged to push the best analytical spectroscopy tools to their absolute limit of detection. And there, you know, you wonder, you can go a long time, and until you run maybe a year's worth of data on a product, and you start to see, I'm not looking at the variation of the plant. I may be looking at the variation of my tax. And now I don't really know what I'm shooting. And that can get pretty scary. So as we take the product from the gas to the solid and start to put it in a form function that goes to the customer, that's where the data quality starts to get a lot looser. But only because we're really limited by our methods and our testing.
And you also mentioned like the fee for electricity are very during time, right? So the rate is fixed, right? You know that now what's the cost rate, data what's the cost.
Right. I mean, that when the energy demand in Michigan is high, the rates go up. When the energy demand goes down, the rates go down.
Okay.
And there is correlation, you know, of course in the summer, right? They tell everybody at home, run your washers and your dryers and your dishwashers at night, because air conditioning isn't running so hard. Well, it would be nice if we were only limited by that, but it's the same flavor, but on a much more complicated.
So the price is not determined freehand. They will not tell you next week the price is this way.
We have some a priori knowledge of how the price can fluctuate, but it's not exact. We don't say, you know, on Friday at 6 o'clock, the rates are going down 50%, and they're going to come back up Sunday at 5. No, it's not quite that accurate. Plus, you know, we have such a large plant. One way to think about it is we have to stagger our operations. There's just not we can't run everything in parallel because there's not enough electricity in Michigan. So we stagger them, start them strategically so we can run as fast as we can. But, you know, that strategy ain't always in sync with the energy costs. And then we got to harvest and things get delayed. Sometimes, you know, they open up one of these reactors and they're bringing up the char and it swings over and it hits one of the rods and you get this wonderful domino effect. And it makes an immense mess. Tons of silicon is a huge mess. It takes a lot of time. And of course, it slows down the operation. So then we get way out of sync from our schedule. So how do we get back on track? What's the most efficient path? Well, right now, we play a little bit with Excel spreadsheets, but there's probably.
So many different things could affect yield. I suppose environment is one of them. For example, humidity, temperature. How dynamic is that? Is daily cycling of temperature an issue? Is seasonal humidity an issue?
We're probably influenced on no more of a scale than seasonal.
Seasonal.
Yeah, there are seasonal trends for sure. The magnitude of the variation is not consistent.
So you've actually looked at the data even through the course of the day and not seen variation.
Well, nothing in our operations. Nothing happens on a day. A day is a very short period of time. We talk about days. You know, our turnover, our cycle time in any one process flow is anywhere from 5 to 7. So a lot of things can happen in 5 to 7.
But even if you have a much longer period for that 5% drier period or something, it seems to me that will cause some influence. If you don't have a compensation.
Yeah, on a global, when I look at the plant as a whole, we do see trends that are seasonal. Of course, we all live in Michigan. Seasons don't happen the same way twice in 2 years, right?
Yeah.
So sometimes they can linger a little longer into the next season. Sometimes.
So to the earlier question about yields, then, are there dynamic things that you would imagine doing on that scale of 5 to 7 days to try to influence yields to compensate for some effect, whether that's environmental, whether that's gas mixture, impurity in the gas, or some particular dusty event, or whatever it is? Are there things you might do dynamically to compensate for that, or are you just left with, well, we just have to be aware and throw this batch away?
No, we try to stay ahead of it. You know, every year we look at root cause analysis for all of the yield losses that happen over quarter by quarter, and so hopefully when we start to see a early fingerprint of the trend that we've seen before, we can take the appropriate action.
So when we hear an interest in sensor analysis, should we also be hearing an unspoken interest in controls?
Yes. So we have to turn that into feedback, right, at the end of it. And for us, now on a control scale, we definitely control on a hours level, right? Not a. Our processes, the way silicon grows in a Siemens reactor, is take a step back and give you a little CVD talk. You start with a very high open volume in the reactor when we start to grow, because we just have these little filaments. But by the time we're done, those little filaments come out to be rods this big. So as the process progresses, the volume in the reactor is changing. The power and radiation effects in the reactor are changing. And how we manage those changes all impacts what we get. So we have control concerns on an hourly basis, a daily basis, a weekly basis, a quarterly basis. All of it. And that's just CVD. Then there's all I think that can happen. Analytical measurements at the part per trillion level. There's again, bad day, humidity in the clean rooms. The one problem with silicon is it just loves impurities. And to test impurities, we have to transform our polysilicon into single crystal silicon, which loves impurities more. I mean, you blink an atom of copper and a piece of single crystal silicon goes right in. And then you got to get that. So it's a very intertwined, complex operation.
In terms of, if you look at it year to year, is your yield or impurities pretty constant now, or are there continual improvements you're still seeing here?
No, we have, especially over the last 5 years, made really nice gains in a plant that is we're a very successful business. But so if you've done any yield engineering, You know, when you have a 50% yield, it's usually pretty easy to figure out a way, relatively speaking, to get to 60%. When you're at 80 or 90% yield, getting to 92% is harder than it is to go from 50 to 60. But our team does a great job. But it's right now, we want, as our business has changed, the historic business in polysilicon was a very specialty material for many, many years, and it claimed a very high price in the market. There were so few people to make it. Over time, more and more people got it, especially when the solar energy boom happened in 2010. And then all of a sudden there was a glut of polysilicon. So the business has gone from what I would call a specialty materials business now to a commodity business. So we might not, when it was a special material, we might have been happy with a mid to high grade yield output. Now today, we want every line drop in the stuff because that's how we stay sustainable.
Yeah, I guess, we're bothering you with the yield questions and stuff, but sometimes
Yields a lot of impact.
it's like difficult to wrap your head around because, I mean, the key problem is energy consumption. So I'm sitting here and say, well, when you look at a process improvement, using something that was made in the 60s, and do the material, with lower energy to begin with, wouldn't that bring the better cost savings as opposed to trying to catch a problem in the fat sooner? But I guess we look at that as well.
Well, I would say, again, we looked at, as I showed the example, was 60, it's 50 years, right? 50 years of development in Siemens reactors. We've done pretty good to manage the energy to the point where we're very efficient. But again, we talk about energy in our plant in kilowatt hours per kilogram of material made.
How much is that?
In the industry, for a Siemens reactor, a very common number is about 50 kilowatt hours per kilogram of material. So then you can find that on the web anywhere. And depending on the reactor design and the management strategy, that can go up or down, maybe 5 to 10 kilowatts. And the process too. The bottom line is, if you take that number and multiply it by 20,000 times the cost, you can see why we're very concerned. Half a kilowatt hour per kilogram to us is huge. The very interesting thing about doing manufacturing on this scale is you can save something at 0.5% or 1% when you multiply it by millions of kilograms. Well, that's a lot of money. Every little gain translates to a big impact on our business.
What kind of machine learning techniques are you using in this case?
Today?
Yeah.
None.
None.
No,
Okay.
none. We are literally 6 months
Okay.
into data analytics. So as of the end of this November last year, we were Excel.
Oh.
And we got our software in, and we partnered with a company, very large company, well established. And our team now is just learning how to use this, right? And they're starting to think about things differently, because the nice thing about these data analytical packages is they will take your data from many sources and they'll process it for you, and they'll say, you might want to look at it this way, you might want to look at it this way. And we can start to compare data sets that before were extremely cumbersome to pair. Well, you gotta learn how to use the software. It's very, you've ever moved from Excel to a data analytics system, some of it's the same, but most of it ain't. And you gotta start thinking differently, how you approach problem solving. And we're at the bottom of the learning curve. Our team's doing real well, but like I said, we all gotta run a plant too. we realize we can't do this on our own if we want to capture the benefits in such a way that we can have the right impact.
Yeah, I want to ask a different question. Previous about use. How about maintenance? Like those parts need to be maintained. So
Absolutely.
What's the strategy you guys maintain? You schedule some time, or you predict based on conditions?
We have very, very well defined preventive maintenance schedules. We literally have to close off and shut down the plant in sections every so many years to replace parts because we know where. I mean, all of the gases and everything we use are extremely corrosive. There's no surface that is going to be inert to our chemistry. Mm-hmm. It's only a matter of how long until it dies. And then that gets complicated by the fact that, too, anytime you open up the loop and you let a little water vapor in when you got right, it just contaminated more. And you don't really know how much got in So you don't know if that's affected your lifetime or your components. So really, we can only look on very long time scales to try and estimate what our PM schedule will be. These reactors are changing, aging. And how can we get better at putting feedback from our PM in and everything to our process and looking at the variations, saying, really you should be doing maintenance more often. Or maybe you can do it a lot less often and save your companies. Today it's very much empirical based on 50 years of work. That's great.
You're selling into both solar photovoltaics and microelectronics.
Mhm.
I've read that solar PV now actually exceeds.
Oh, the solar, it's 3 to 1.
So
Easily.
Does that change the way you do business?
Well, in the beginning of the solar boom, it did. Because in the early days of solar, when multicrystalline cells were the desired output, their requirements for polysilicon were, I would say, much wider, easier to meet than the microelectronics. Now, fast forward 10 years, people in silicon are very, very smart. They figure out now, when you go back to the 60s, the first solar cells made by Jerry Ovchinsky down in Plymouth, and everything, what did they use? Single crystal silicon. It's expensive. They showed the premise could work. Of course, then these guys start making multicrystalline solar cells with direct solidification. They got some very good results, but you can only get so far with a defect. The defects are in multicrystalline cells. So at the same time, you got these guys that are real smart. And they say, I can figure out how to get the cost of a crystal down. And they play with it, and they play with it, and they play with it. And you come fast forward to 2018, they got really good. So now they can make solar cells out of single crystal material. So at cost and basically dollar per watt efficiency levels that are almost better than the multi-crystal. And so their trajectory, and what's more, from science tells us in the multicrystalline solar cell area, we're pretty much at theoretical limit. Whereas in single crystal cells, there's a lot of headroom yet to go. So now that these costs are getting very competitive, the guys who are making the single crystal cells, I need better silicon. I can't use the junk we were using for multicrystal. So now we see the microelectronics industry and the solar industry, though the microelectronics guys pay up here, the solar guys pay up here, but they're moving toward each other. And the real scary thing is what'll happen when it gets here. Right? Do the semiconductor guys say, I think I'll just buy this stuff now, it'll work for me too? That would be disastrous. Right? But then we're going to lose our margins there. So this is a cataclysmic event that is inevitable in the next 5 years. We all wait to see what happens. My guess is we'll meet somewhere in the middle. Doesn't take a genius to figure that out.
Sorry, so many questions. You mentioned like products really hard to measure the quality, like it take weeks or days.
Days.
So right now, like in the industry, I feel that they do have some virtual metrology. Right? So they measure some easy measurements about the product, which can be pretty predictive about the final quality.
It's not been our experience.
Okay.
No. So, because there are so many parallel sources of impurity, and there's no way to do non-destructive interrogation of the silicon to assess the impurity. This is what makes the measurements. Now, if you had a very impure, metallurgical grade silicon, things like this, which is very impure relative to what we make, then interrogation could be very bad. We can use non-destructive techniques. But when we're at the sub-part per billion level, all the techniques that you need to use are destructive.
Destructive way to measure.
Yes. I really wish we could look at stuff right when we open up the reactor and say it's good. So anybody can do it. They'll figure out they're going to make a lot of money.
Yeah. Another thing is I want to see how responsive the factory will be. Say for one sensor, they indicate some turbulence in the air. So anything you can do to prevent the turbulence, you can lower flow rates, or if some sensor indicates some part is wrong, you have to shut down the factory, or you can do some.
Well, really, when you consider the scale and number of machines running at the same time, we get a distribution of performance. So the first thing you ask is, based on this distribution of performance, how many tests do I need to make to prove the number I'm measuring is outside of my distribution? That all depends on how wide the distribution is, right? If I have a very narrow standard deviation, delta function, one test is significant if I'm not in the same place. I know I'm not in the same place. But if I have a wider standard deviation, it may take hundreds, if not thousands, of tests to shift the process, especially a process running very close to the measurement. So we're not, while we love instantaneous feedback and control, because of the natural variability of the technologies we use, we're happy to fix the problem next week. It'll save us a lot. But it literally takes weeks. Now, if we could have a software system, of course, we have 25, 30 years of data stored. And so we can go back, right, and interrogate data and look for trends that could help us know better what we want to do next quarter. But of course, over this period of such a long time, things have changed. And we've made improvements. We've changed the way we do things. So that on the Windows, really, a backlog day maybe are only single years.
So you mentioned like the yield change with the weather. So, and I remember this kind of industry that you are really control the environment is really good inside, but still outside environment still affect the yield and the quality.
Well, imagine you got this big refinery, pipes everywhere, and we're running gases under conditions near what's called their triple point off, where they can switch between gas and liquid phase changes. And so when the weather is cold outside, the fluid dynamics in our pipes, they change. And impurities move differently because they all have different properties. And how that all gets transformed into what injects into the system when we're trying to grow is seasonal. And when we talk about yield changes, yield is the product of, I would say, maybe 24 test responses that all got to be successful at the same time. So in summer, failure mode may be different than in the winter versus the spring. So we have to be agile to understand this, what dominates loss seasonally, and be ready to adjust for that as best we can.
That's one question. I'm just curious about how much the gap is the current protocol, like processing protocol, versus the one you want to get from machine learning. Because currently you probably don't use machine learning, and then how do you decide what kind of like a procedure to make the production? Pretty much I find error, or there's
No, we can look at it statistically. So I know my plant's running at a certain level of performance, and I can look a year back and look at the variability of the plant, say with respect to energy. And I have a mean level, and I got some processes, some part of the plant's running above the mean. But I'm all doing the same thing everywhere. So if I can take 1/2 of that operation that's above the mean down 50%, I save a fortune. And the same thing is, I have another part of my plant that's running below the mean. That's running very energy efficient. But again, I'm presumably running the same process to the best of our ability. So why are these machines running so efficiently this quarter? If I could run everything, if I could shift my mean down to where those guys are, there's a huge impact. So we judge our trajectory and improvements based on that variability. So how much of that variation can we reduce? Or how can we shift the mean and achieve a targeted cost reduction improvement each year? And that number varies depending on what part of the plant we're using. Whether it's the refinery or the CVD operations or the post-processing. So every year, you sit down every December and the accountants go, you'll operate here. And our challenge in the science and technology area is to figure out how to get there. Other questions? Happy to answer any questions. Very good discussion.
Okay, so you mentioned like the environment, direct effect to the pipe, right? So outside the pipe, does that have any sensor inside the pipe you can monitor the condition?
Not any that'll live very long.
Okay.
We're happy to get valves that live a long time. The environment is so corrosive.
So
now Thomas can make us a diamond diode. we can put in there to measure the flow and temperature. Then I might be able to get a sensor that we can track. But you know, we have to everything's relative, right, Don? Other questions? Interests? If not, again, I thank you for your attention. Appreciate your time.